Around the 16th century, the track and field event pole vaulting started to develop in ancient Greece, where competitors sprinted a distance and used bamboo poles to leap over heights. Today, its definition has not changed by much, but specifically, the goal is to jump over height, using only a pole in the runner's speed, strength, and strategy. Runners sprint a set distance holding a carbon fiber pole, and after sticking the pole in a board stop next to the height in which they jump over, the pole bends and their body thrusts over the height to be cleared or not. So, considering modeling a pole vaulter's mechanism of motion using in-class physics models, the system schema would include the ground, the pole vaulter, and the pole, where the pole vaulter is in contact with the pole and the ground. Additionally, for this case, it is important to include the pole vaulter's energy pie chart showing that the runner ends a run with mostly kinetic energy, and when the runner releases their pole, it's more potential than kinetic. Then lastly, in the air, at their peak, it's all potential energy. Therefore, the relationship and how pole vaulter's height can be found using physics modeling shows that kinematics plays a much larger role than I'd imagined in a sport that I tried in middle school. Now, although I wasn't the best, I was always fascinated to watch how other students were able to thrust themselves over the height to clear the pole given the speed at which they ran, which is a variable I thought would not have as much impact on the pole vaulter's height as it does. And from hearing all about a friend of mine on the MSU pole vaulting team and the news last year, I wanted to investigate the physics behind pole vaulting. But with that said, it turned out that I was a much better mid-distance runner than a pole vaulter. Now, although competitors only get 3 attempts to clear a certain height, the runner's theoretical height can be determined by using the runner's mass and initial speed when combining kinematics and energy variables, specifically equations used in pole vaulting in reference to our class notes on kinematics and energy, potential energy, kinetic energy, and a kinematics equation for the height in which the runner could jump along with initial velocity for the runner. Because you see that in particularly after using kinematics equation to find the runner's velocity, one is able to determine the possible height the runner is able to achieve using the initial velocity by setting potential energy and kinetic energy equal and solving for the height that way. That is the point at which the maximum height is when the kinetic energy is 0 and all kinetic energy is converted to potential, even though this may not actually occur in reality. Now, for example, say that there are 2 pole vaulters competing, pole vaulter A and pole vaulter B. The height that they must clear is 4 meters. So if pole vaulter A had a center of mass of about 1 meter and ran about 7.8 meters per second, whereas pole vaulter B with the same center of mass but a different speed at 9.3 meters per second, pole vaulter B would be able to clear the height, whereas pole vaulter A would not be able to. We see that the pole vaulter's velocity is quite involved in predicting the height in which the pole vaulter can clear. So if this were to be the third trial for each, pole vaulter B would be able to clear their height and move on to the next height, while pole vaulter A, despite not clearing the current height, will use the height reached before this current height. In conclusion, it is safe to realize that differing the initial speed of the pole vaulter can predict the height in which the pole vaulter is able to clear, combining kinematics with energy transfer according to in-class work and sources used. However, because this is a complex sport on the body, there are still other variations and variables to consider when determining how an athlete is able to clear a certain height or not, such as muscle strength and performance, flexibility, and core strength.